So what I propose to do is just to deal with this last question part 7 part B, and then question 8. So we'll have a look at those, deal with any queries that come up along the way, and then we'll see if we've got time remaining. I can find a question from somewhere else, or I can just answer any queries that people have. Might be one or two things we might want to look at on the screen. So I've got up to look at if we need it. Any questions? Just following on from the last hour, that's all. Okay then, let's have a look at 7 part B. So I completed 7 part A, I believe, that right? Yeah. Bases for the kernel and the image. So 7 part B is a little proof question on linear algebra. Okay, so what's it asking us to do? It says if an n by n matrix, so square matrix, has eigenvalue lambda with corresponding eigenvector x, then prove that x is an eigenvector of the matrix A to the power k, corresponding to the eigenvalue lambda to the power k. So this is telling us that if we understand the eigenvalues and vectors of a certain matrix A, we then also understand the eigenvectors and eigenvalues for any power of that matrix. Now it's, yeah, okay, let's have a go at this. So the first question you've got to think about, and it's not addressed explicitly in the question, but which k is the question talking about? Perhaps I would have liked to have seen maybe specifying exactly which k. But so the natural thing to think about is, well, positive integer values. K equals 1, 2, 3, etc. But that formula, the question, as it's stated, actually makes sense, but actually the result also applies for negative integers. So, well, 5 marks, maybe he wasn't expecting the proof for negative integers as well, but it's hard to tell when it's not explicitly stated, and it is true for negative integers, -2, -3, etc. But provided what? There's an extra condition we need to impose in order to make sense, in order to prove this for negative integers. Anybody? What is provided something? What do we mean by the matrix A to the power -5? What do we mean by that? It's clear what we mean by the matrix A to the power +5. It's just A times A times A times A times A. Five factors of A multiplied together. A to the power -5 refers to the 5th power of the inverse matrix A inverse, multiplied by itself however many times. So as long as we know that such a matrix exists, as long as A is invertible, as long as it's non-singular, a non-zero determinant, we can also make sense of this question for negative integer powers of A. i.e., A is non-singular. Okay. Here, okay, so let's deal with the positive integers first. We'll prove this. So what proof technique are we going to use? We were trying to prove that x is still an eigenvector for a to the power k associated to the eigenvalue lambda to the power k. So that's a set of separate statements indexed by the positive integer k. So that immediately suggests one proof method, which will be proof by induction. Okay. So we could use as the base case, we could use k equals 0. So we're going to prove this by induction. The base case is a equals 0. Here, a to the power 0 is by definition the identity matrix. The identity matrix, I mean, what eigenvalues does the identity matrix have? Eigenvalues of the identity matrix? It's a good pop question. Only one reasonable answer. Well, only one or two. So an eigenvalue, remember, is you're looking for situations where the matrix times a vector is equal to a scalar multiple of that very same vector, where the matrix is just acting as a stretch or a contraction in the same direction as that particular vector. Well, the identity matrix is an extremely special matrix. This satisfies for every vector x, ix is equal to x. Basically, every vector is an eigenvector associated to the eigenvalue 1. Yeah. So the identity matrix has eigenvalue 1, and every vector is an eigenvector of it. So it's got an n-dimensional subspace, n-dimensional eigen subspace associated to the eigenvalue 1. So x is an eigenvector for eigenvalue 1, which we can represent as lambda to the power 0. So the base case is true, basically. So assume that a to the n, n is slightly, I won't say a to the n because n is we're told in the question n is the size of the matrix, so I won't do that. So assume, let's assume a to the k times x equals lambda times lambda to the k times vector x. That's the induction hypothesis. So how do we move on to the next? In the middle of a proof by induction, so you assume it's true for some integer k. You want to move to the next one, k plus 1. How do you get the equation involving the matrix power a to the k plus 1 out of this? Very clear way to go, thing to do to get the matrix a to the power k plus 1. We've already got a to the k. So what we do is we just multiply both sides of this by the matrix A. Yeah? Because that very clearly on the left-hand side, because matrix multiplication is associative, I can first multiply A by A to the k, getting A to the k plus 1 times vector x. Another property of matrix multiplication, you see here we have some matrix multiplication going on, the matrix A times the vector x, and in the middle of it there you've got a scalar, lambda to the power k, a scalar multiple of the vector. Well, scalar multiplication in the middle of a matrix product, the scalar multiplication can actually commute with all the multiplication of the matrices. So the scalar can slide around to any position in the product. So I can take the scalar out and have it multiplying the matrix product A times X. So these are properties of matrix multiplication. So you still got a to the power k plus 1 times x. But of course, x is this special eigenvector associated to the eigenvalue lambda. So this is lambda to the k times lambda times x. Okay? As ax is equal to lambda x. So this gives us the result we want. A to the power k plus 1 times vector x is lambda to the k plus 1, which is indeed the result for the next value of k, after the one we assumed, a to the power of k. Which is the required result for k plus 1. So we assumed it was true for some integer k. This was some integer k greater than or equal to 0. Some k greater than or equal to 0. From that assumption, it then automatically follows that it's true for the next one, true for k plus 1. We've already established it's true at the beginning, in the base case, k equals 0. So by induction then, this is true. This is true for all k greater than or equal to 0. Yeah. Quite a nice induction proof. Base case is kind of obvious. There's nothing to prove in the base case, really, because you're just talking about the identity matrix. So every vector is an eigenvector associated to the eigenvalue 1. 1 is the same as lambda to the power 0. So the base case is kind of just observation or interpretation. And you make the assumption, and you prove the next one, k plus 1, and then you conclude it's true for every one of those x's in that range then by induction. And note we have indeed used the basic assumption that x is an eigenvector, eigenvalue lambda. We have made use of that, as we should have expected to, in the course of the proof. The negative integers can be handled in much the same way. So for the negative integers, the base case is the same. Still k equals 0. But this time now we want to go in the opposite direction, down through the negative integers. So but now, yeah, so except we're not going to be multiplying both sides by a, we're going to be dealing with the inverse matrix A. So assuming A inverse exists, which necessarily means that the eigenvalue we're talking about is non-zero. If a matrix has 0 as an eigenvalue, it means it has to be a singular matrix. Because if it has 0 as an eigenvalue, then there will be non-zero vectors x that get sent to 0 by multiplication by the matrix. So the matrix multiplication is not one-to-one, it's not injective, so the matrix will not be inverted. So invertible matrices necessarily have non-zero eigenvectors. I need lambda to be non-zero, so I'm going to be talking about the reciprocal of lambda. Okay. So ax equals lambda x. This implies you simply multiply both sides by a inverse. And that will imply that 1 over lambda times x. So here you get A inverse A, which is the identity. So the identity times x is x. I get a lambda over here. I just stick it over to the other side. 1 over lambda equals A inverse x. So i.e., x is an eigenvector of the matrix A inverse associated to the eigenvalue 1 over lambda. And that's why we needed to make the remark that lambda was not 0 in this case, in the case where A is an invertible matrix. So we're going through the negative integers k. So now assume that A to the k times x is equal to lambda to the k times x for some k less than or equal to 0. You know it's true for k equals 0. That's the base case, the same base case as before. And now multiply both sides by A inverse. So A inverse times A to the K times X equals A inverse times lambda to the K times X. And as before, this gives us A to the K minus 1 times X equals lambda to the K minus 1 times X. Because that lambda to the K slides out to the front of the product on the left, then you've got A inverse times X. We've already described how A inverse times X is 1 over lambda times X. So you've got lambda to the K times 1 over lambda. So you've got lambda to the K minus 1 times vector X, which is the result, which is the required result for the integer K minus 1. So we're starting at the integer 0. We assume it's true for some K less than or equal to 0. And then we're able to derive that it's true for the next one in the negative direction, in the K minus 1. So by induction, then, it's true for all. By induction, result is true for all negative K. Negative integers K. You don't normally see induction like that going through the negative integers. Normally we start at some base case and go upwards in the positive direction, but equally well, you can go in the negative direction. And it's exactly the same principle. It's true for base case, and you assumed it's true for some statement in the range, and then it's true for one in the next. One click on, so to speak. So the principle of induction says, therefore, it's true for all the clicks, for all the negative integers. Okay, so that's a pretty good treatment of 7 part B. I suspect, since there's only 5 marks going for it, and it didn't make any specific reference to negative integers, I'd expect just the proof for the positive integers might have gotten the full marks there. But, you know, you could show good understanding anyway, if it wasn't explicitly asked for, still, just to make some remarks in the negative direction. Okay, any questions? So yeah, so an interesting point raised by that is, remember, eigenvectors by definition, so the definition of an eigenvector is always a non-zero vector, but it's perfectly possible for a matrix to have a 0 eigenvalue. So 0 is a legitimate eigenvalue for a matrix, perhaps, if it has that. That just means that if 0 is an eigenvalue for a matrix, it means there will exist non-zero vectors that get sent to the 0 vector by multiplication by the matrix. Okay. Any related queries? So that question dealt with transformations, kernel image, eigenvectors, and so on. Any associated queries to those? Anybody like to ask? Okay. In that case, then, we may as well proceed on to question 8, which is on the subject of inner products and associated things. Okay, use the Cauchy-Schwarz inequality to find an upper bound for this integral. So the integral we're looking at is the integral square root of 4 minus 7x dx. Okay, so we need to look at the Cauchy-Schwarz inequality for this. Cauchy-Schwarz inequality is an inequality about the of 2 vectors, and it relates it to the norms of the vectors, or the inner product of the vectors themselves. Okay, the Cauchy-Schwarz inequality is that phi of u(v), square of this value, is always less than or equal to the inner product of u with u multiplied by the inner product of v with v. product. Okay, that's what it looks like in general. How is it going to look specifically here? What is the inner product that we're talking about here? Well, we're talking about integrating real valued functions over the interval -1 to 1. Yeah, I say real valued, but I have to be a little bit careful there because the subject of the square root there, 4 minus 7x, that's going to be negative some of the time, won't it? Yeah, as x gets close to 1, this is going to be close to 4 minus 7, which is a negative constant. So actually we're looking at complex value functions here, actually. However, that won't stop us, I don't think. Yeah, so there's a slight complication here. I think we'll be able to proceed that complication in that the integrand, if you want to have it well defined over this interval -1 to 1, the integrand takes complex values in general. Nothing crazy there. Yeah, as x gets close to 1, 4 minus 7x is going to be negative, so you're going to have to admit complex values there. But I believe the Cauchy-Schwarz inequality in these inner products, you can set these up on complex valued functions. And the standard inner product, we'd still be dealing with the standard inner product here. But the standard inner product phi in this context is phi of f of g is going to be the integral from -1 to 1 of the product of the two functions f of x times g of x dx. Okay, so now how can we adapt that to this integral? Well, so we let the function f of x be the square root of 4 minus 7x, and the function g of x be the constant function 1. Then I is indeed the inner product of f of g. And by the Cauchy-Schwarz inequality, this is going to be less than or equal to, see I've taken the square root of both sides here, less than or equal to the square root of 5u with u times, or just the square root of the whole thing, times 5b with b. Sorry, f with f, g with g. Switch to the f's. It's more natural to use letters f and g for functions rather than u and b. But yeah, you could use u and b as well. You can stick with u and b. And the point about the point about this whole exercise is this integral it's not possible to do this integral in a closed form. You can't actually evaluate this and get in terms of some nice function of x, simple enough function of x. So what the Cauchy-Schwarz so you would have to, if you wanted to evaluate this, you'd have to resort to some kind of numerical integration. But what the Cauchy-Schwarz inequality allows you to do is, in advance, at least being able to get some control over I, to have an upper bound for its absolute value. Okay. So this thing here we can do, this is going to be the square root of phi of f with f. It's going to be the integral from -1 to 1 of 4 minus 7x dx. And the other one is just the integral from 1 to 1 of g times g. Well, g is just the constant function 1, so this is just the integral dx minus 1 to 1. So this integral here gives you 2. The integral dx is just the length of the interval that you're integrating across. And then this integral, well, we can integrate 4 minus 7x easily enough. Just goes to 4x minus 7 over 2x squared. And we're going to evaluate that at minus 1 and 1. And then take the square root of all of it. Seem okay? Now the x squared bit isn't going to contribute anything, because when you evaluate it at the top and lower limits, you're going to get the same value in the x squared bit. So when you subtract them, they're going to cancel out, okay, because it's squared. So you're just going to get 4 when you do x equals 1 minus 4 when you put in x equals minus 1. So it's going to be 4 minus 4, so it's just going to be 8. So what you got here is square root of 16. 4. Nicely enough, comes out as 4. So actually, because it's complex value, I can't say I is less than 4 because it could be complex value. Yeah, so I think the correct way to treat this is to talk in terms of absolute values, magnitudes, because these things could be complex valued. You can't talk about one complex number being less than another one because they're not ordered. They're in a two-dimensional space, but you can certainly talk about their absolute values. So I think when you take the Cauchy-Schwarz inequality, and these are complex valued inner products, and when you take the square root of both sides, you're going to be talking about the magnitude of the thing over that. So in conclusion, we can say that the absolute value of our integral is less than or equal to 4. Okay, question B, part B. This is a piece of bookwork here. So this relationship amongst the norms for an inner product phi in a vector space V. So the statement is very general, not told anything in particular about the vector space or the inner product. So phi an inner product on a vector space V. We want to prove that for every pair of vectors u and v, little u and little v in capital V, that this relationship holds. The square of the norm of u plus v plus the square of the norm of u minus v is always equal to 2 times the square of the norm of u plus 2 times the square of the norm of v. And the way into this question is all about how norms in general are defined in terms of an inner product. So the norm associated to the inner product phi is there in definition 4.2, where the norm of a vector x is by definition the square root of the inner product of x with x. Okay. So these statements about the squares of norms really statements about inner products of vectors with themselves. Okay. So we will prove this using this definition of norms in terms of inner product, in terms of phi, and the defining conditions or properties of the inner product phi. So an inner product, so that's what I'm referring to there. So there's three properties here. Some or all of these we're going to make use of. 1, 2, and 3. But the inner phi, the inner product is linear. First variable, it's a symmetric function. Two vectors, so combination with 1, that's going to mean it's linear in the second variable as well. And 3, the positive definite property, although I don't think that's going to come into it. I think here we're just going to use basically linearity in both of the variables. So by combining properties 1 and 2, from here, phi is linear in both variables. Linear in both arguments. The inner product phi has two arguments, first argument and second argument. So we basically start on the left-hand side, the norm of u plus v squared, plus the norm of u minus v squared. So you pass to the equivalent statements in terms of inner products. Okay, is any difficult to read there? No? Okay. So the norm of this vector squared is the inner product of this vector with itself. And the norm, the square of the norm of this vector is the inner product of this vector with itself. So there we're using the definition of a norm in terms of the inner product. And now we're going to use linearity in both the variables. See, this one is going to give you phi v with u, plus phi v with v, plus phi v with u, plus phi v with v. So that's what that one gives. Then the second one gives phi of u with u plus phi of give minus phi of u with v minus phi of v with u. And finally, phi of minus v with phi of minus v, but by linearity, both of the minus signs come out to give you the plus sign, plus phi of v with v. So that one there is the second one. Okay, so the first inner product in the previous line, previous equation, gives us the first line, the last equation, and the second inner product gives us the second line. And you can see there, you can see there that there's a fair amount of cancellation that happens there. So you got positive and negative terms, both the same, so they cancel, and then these two terms are the same, these two terms are the same. This gives you 2 times phi of u with u, plus 2 times phi of v with v. Yeah, the others are cancelling. So the justification for getting to here was by linearity. Got a linear combination in both argument positions to phi. So you're just basically expanding that. And of course, the inner product of u with u is exactly the square of the norm of u. The inner product of v with v is exactly the square of the norm. That's true by definition of the norms. And that's yeah, that's all that's involved in proving that. Basically, just combining the properties of the inner product with how norms are defined in terms of inner products. Okay. Then on to C. So C was the kind of last topic we talked about in the linear algebra, which was the Gram-Schmidt orthogonalization process, which takes an arbitrary basis. An arbitrary basis will just be a linearly independent spanning set for the space. But we really like it. Well, we really like it in particular when bases are really nice, which is that they're orthonormal. That all the basis vectors are mutually orthogonal to one another, and they all have length 1. That's really nice. But here, you're just asked to go as far as the orthogonal bit. So those 3 vectors, it is claimed, are a basis for D3R. We'll take that for granted, that they are. So we want to apply the orthogonalization procedure to produce the associated orthogonal basis for this. Now we could immediately just write down the standard basis for R3. It's going to be an orthonormal basis for V3R. But the point here isn't in how to get to. That wouldn't really satisfy us in just kind of throwing down the standard basis for this space, which we know. Producing the associated orthogonal basis, it preserves a lot more. So the vector space generated by the first vector will still be the same as the vector space generated by the first vector in our new set. And the vector space spanned by the first 2 vectors here will still be preserved by the vector. It will be the same as the vector space spanned by the 2 vectors in our new basis. Okay. So when you specify a basis as an ordered set of an ordered sequence of vectors like this, you're also specifying some kind of stratification of the space. So some kind of ordering in how you define the space. So in this case, a 3-dimensional space is first a line, then a plane containing that line, and then finally stepping up to the 3-dimensional space containing that plane. Well, this new basis that we're going to put down is going to be an orthogonal basis. The vectors are going to be mutually orthogonal, but they'll still have that same stratification or construction of the whole space. The line spanned by the first new basis vector will be the same as the line spanned by the first basis vector here. The plane spanned by the first 2 new basis vectors will be the same as the plane spanned by these 2 vectors. So that's the information that's observed. So we're following. Here's the specification of the process. So the vectors u1 up to un are the old basis, so that's what we've got down here. So following the procedure, or following the algorithm in the notes, with u1 equal to these 3 vectors, so u1 is 1, 2, minus 1, u2 is 1, 0, 1, and u3 is 0, 0, minus 1. What's the phi? What's the inner product? We need to get specific. We're going to be doing calculations here. We need to be specific. And using the standard inner product, on V3R, namely the dot product. So the nice familiar inner product is simply the dot product of 2 vectors. So the sum of the products with corresponding components. So we build a new basis, we build a new orthogonal basis. V1, V2, V3. Should be underlining my vectors here, but anyway. So you follow this, and the first step is easy enough. V1 is equal to U1. Because we want the line spanned by our first basis vector to be the same as the line spanned by the old one, so we just simply take the old one. But now it's in the construction of V2. So V2, so our first guess, our first step in the construction of V2 is to simply take U2. But in order to ensure that it's going to be orthogonal to V1, we have to subtract, this quantity, which is a scalar multiple of vector V1. So we're subtracting a little bit of V1, so to speak, and we're subtracting this quantity here, phi of U2 with V1, divided by phi V1 with V1. This quantity here that we're subtracting, this scalar multiple of V1, this is actually understood as the projection. This is the projection of V2 onto V1. That's the projection of U2 onto V1. So we started off with this vector V1 in this direction. The vector U2 is not necessarily orthogonal to this, but once we subtract this little bit here, so this is the orthogonal projection. That little red vector is the orthogonal projection of U2 onto V1. Once you subtract it, that means this vector here is going to be your new V1, this red vector, and it will be, by design, it will be orthogonal to sorry, that's going to be the V2. By design, it will be orthogonal to the V1. Because you started with U2 and you just deleted the portion of U2 that goes in the direction V1. So there'll no longer be any part of V2 that goes in the direction V1. So in other words, it's going to be orthogonal to it. So this is, okay, we know what V1 is. We know what U2 is. It's 1, 0, U2 is 1, 0, 1 minus, and we know what V1 is. V1 is U1, which is 1, 2, minus 1. We just need these two inner products. So these are dot products. Dot product of V1 with itself. This is V1 here. The dot product is just the sum of the squares of the components in U1. So that's 1 plus 4 plus 1, 6. And then the dot product of U2 with V1. Well, V1 is equal to U1, so just the dot product of U2 with V1. That's simply 1, 2 times 0, plus minus 1 times 1. Ah, interesting. So that's actually 0. So actually V2 actually happens, in this case, to be equal to U2. So I hadn't spotted that yet. In fact, U2 was already orthogonal to U1, it appears. Yeah. You take the inner product of our V2, which is the same, happens to be the same as U2, it was already orthogonal to V1 because they had a dot product 0. But in general, there will be a non-zero projection bit to delete here. So that's good. So we've got our V1, we've got our V2, so we can now write down our V3. We follow the same principles. We start off V3 as U3, and we just want to subtract from U3 the bit of it that goes in the directions V1 and V2. So the bit of it that goes in the direction V1 is a scalar multiple of V1. It's the inner product phi of U3 with V1 divided by the inner product of V1 with itself. And you also subtract off the bit of U3 which goes in the direction V2. And much of V2 is this ratio here. Okay, so I believe that's the third of the Gram-Schmidt theories. So you just need to work these out. U3 we've got is 0, 0, minus 1. Now there will be something to delete here because this vector is not orthogonal to V2. It's not orthogonal to V1. So there will be some non-zero stuff to subtract in both cases. V1 is 1, 2, minus 1. And the coefficient here is the inner product of V1 with V1. Which, as we saw before, was 6, and the inner product, the dot product of U3 with V1, so that's U3 with that U1, so that's just 1, I believe. Yeah. And you also subtract V2. V2 is this one here, 101. The inner product of the dot product of V2 with itself is 2. And the dot product of U3 with V2 is again -1. Minus. So you just got to be a little bit careful. There's a few minus signs floating around. So what are the components here? So you got nothing. You got minus a sixth. And minus, so plus a half. A half minus a sixth. A half is 3/6. Minus 1/6 is 2/6, which is a third. 0 is nothing. Minus 2/6 plus nothing in the second position. So it's just minus 2/6. So in other words, minus a third. And the last component, so it is, you've got something here, -1, plus a sixth. So that gives us 7/6. And then plus an extra half, plus an extra 3/6. Should give us 10/6. 5/3. All right. So if I've done it correctly, if I've added all my fractions correctly, this vector V3 ought to be perpendicular to both V2 and V1. So if you quickly take its dot product with V, it's not, is it? There. What's gone wrong? Okay, so this is good. So there's checking to do. Can anybody spot where I went wrong? What did I do?
5.3 should be minus the.
That's minus a third. Yeah. So yeah. Oh, I started off at -1. Sorry, I thought in my head I start off at +1. So start off at -1. Yeah. So this comes out as minus a third. Thank you. Okay, with that correction, you can see that this is perpendicular to V2, so when you take the dot product with V2, you do indeed get 0. And it ought to be perpendicular with U1 as well. U1 is 1. This is 2 times that. It's going to be minus a third, then plus another third. Yeah, so it does check out now. So V1, V2, V3 are the orthogonal bases required. Okay, so do check the output from those procedures. See, it is easy to go slightly wrong in your calculations.